The acceleration of a particle moving in a straight line is given by a equal to k into 1 minus v squared, k greater than 0, where v is the velocity at any time t. Find an expression for the velocity in terms of t, hence its limiting or terminal velocity, and part B, find an expression for the position in terms of the velocity, hence its limiting position if possible. So for part A, we have a equal to k, 1 minus v squared, and we want to find the velocity in terms of t. So a is going to become dv on dt, which is equal to k into 1 minus v squared. Now I'm going to divide by 1 minus v squared and multiply by dt, so I'll get dv over 1 minus v squared equal to k dt, and then I'm going to integrate both sides. Alright, now the right hand side is quite simple, it's kt, and let me just write it here. Now the left hand side, if I want to integrate this, hopefully you can recognize that this is a partial fraction integral. So I need to decompose these into partial fractions, which would be a on 1 minus v plus b on 1 plus v dv. Now, if you were to go ahead and work out your constants a and b, they would both be equal to a half, but I won't do that in this video, although it's a good exercise to go ahead and check that yourself. So, this is what we have, dv. Okay, and now I can integrate this. This is almost a log, I'm just missing a factor of -1. So if I multiply by -1 and multiply by -1 again, I'll get minus log, should be a half out the front, 1 minus v, and here I'll have a half log of 1 plus v, and I have a constant plus c. Great. Now, we're not given any initial condition or any time t where velocity is something or the displacement is something, so we actually can't work out our value for c. But let's just continue on and see what we can do. I can combine these two logs, and I'll have 1 plus v on 1 minus v. And now I want to write my constant c in a particular way. I want to write it as a half log of some constant a. Now since c is just a constant, this thing is also just a constant, so this is fine to write it in this way, because this c is determined by an initial condition. Although we're not given an initial condition, that's really what the constant is. It's just a constant that's determined by an initial condition. And the same thing here, we could determine a by an initial condition. And then the value of this entire thing here would be equal to the value of this entire thing here. I haven't really changed anything. So I should say just for some constant a. But the reason I've done this now is hopefully you can see that we can combine these logs. I can get a half log of a into 1 plus v over 1 minus v equals kt, and then I can rearrange for v. I'll get 2 kt equal to log of a into 1 plus v, 1 minus v. Alright, I'm going to exponentiate both sides, and at the same time I'm going to multiply by 1 minus v. So I'll get e to the 2 kt, 1 minus v, equals a, 1 plus v. Alright, now let's rearrange and solve, and set v as the subject of the equation. Alright, so that's going to give me 2 e to the 2 kt minus v e to the 2 kt equal to a plus av. Bring this over here and I get e to the 2 kt, bring this over here, minus a, equal to, now as I bring this over here it becomes a positive, and I want to factor out a v from each term. So I'll have v, not an a, oh yeah, I'll have an a, plus e to the 2 kt. Alright, now I make v equal to, dividing by this, let's see, e to the 2kt minus a divided by e to the 2kt plus a. Alright, and this is our expression for v in terms of t. And let's just note here again that a is a constant. A is some constant. Okay. Now, we were also asked for its limiting or terminal velocity. Now, the terminal velocity is the velocity of a particle or a mass or something as t approaches infinity. So, when t approaches infinity, what's the value approaching? The value of v approaching? Well, v is approaching what? This thing here will become exponentially large and will dominate this function here, which is just a constant a. So this is going to look like 2 to the power kt on the top. And on the bottom, the same thing's going to happen. This part will dominate the denominator completely dominating a as this becomes exponentially large, and so it'll look like 2k to the t, and this is something divided by itself, which is equal to 1. And so as time goes to infinity, my velocity is approaching 1, and we should probably put meters per second, but we haven't really been told units, so let's just say units. 1 unit, or 1 units per second. Unit distance per time, that should be what we write, unit distance per time. Okay, so the velocity, the terminal velocity is equal to 1 because we take t as it goes to infinity, and that's the end of part A. Now for part B, let's have a look. For part B, we need to find an expression for the position in terms of the velocity, and then finding the limiting position if possible. So, just like in the first part, we have that a equals k into 1 minus v squared, but this time our expression for a is going to be v dv dx, because we want to find position in terms of velocity. So we need something that relates v to x. K 1 minus v squared. Okay, now I can rearrange, get all my v's on one side and all the x's on one side, and I'll have v over 1 minus v squared dv equal to k dx. And then I want to integrate both sides, and let's see what we have. Here we almost have a log, we almost have the derivative of the denominator on the top. We're just missing a -2, and so I have to compensate by dividing by -2 or multiplying by -1/2. And here I have k, which is just a constant, that's fine. So integrating this will give me half, a -1/2 log of the denominator, which is minus v squared, which is equal to k x plus a constant c. Now again, I'm going to use the same trick as I did in the previous part. I'm going to write this constant in a certain way. I'm going to write it as kx plus a half log of, maybe this time we'll use the letter b. So b here is just a constant. And again, a half log b is just a constant because c is just a constant. It's just a convenient way of writing this so that I can combine it with this expression here. So if I move this over, I'll have -1/2. This will also be -1/2 when I move it over. So as I combine my logs, it'll be a product of the two. So this should be b, not a. b into 1 minus v squared equal to kx. And I'm looking for position in terms of velocity. So that's going to be simple. I'm just dividing by k now. -1/2 k, minus 1 on 2k rather, log of b into 1 minus v squared. Okay, and we also need to find the limiting position if possible. So the limiting position is the position as t approaches infinity. Well, we don't have an expression for x in terms of t, but we do have x in terms of v, and we know the value of v as t goes to infinity. That's what we worked out as the terminal velocity in part A, and that was 1. So, as t approaches infinity, our v is going to equal 1, And so that means that x is going to approach minus the half 2k log of b into 1 minus, well, b squared is 1. And what's this? Well, this is log of 0. Now, log of 0, this is what our log curves looks like, and it's approaching negative infinity as the x value, or whatever the value, as the argument goes to 0. So here it's approaching negative infinity. So this bit here is negative infinity, but I have a negative number here. So I have a negative times negative infinity, and so x is approaching infinity. Or in other words, there is no limiting position. So therefore, the limiting position doesn't exist. And that is the end of the question.